Greetings to everyone. My name is Samuel Mbogwa, and I'm the one who will be facilitating Calculus 1. The unit code is MAT 120. My contacts, the email address, and the telephone number are here, and they've been shared in the portal. And this unit basically will be concerned with the use of the mathematical tools. If I was to define what calculus is concerned with the mathematical analysis of change or movement. And there are two techniques that we do appreciate in calculus. The first one is differentiation, and the second one is integration. For calculus 1, we'll basically deal with the first one, differentiation, and in calculus 2, we'll be making use of the other tool. I've shared this equally in the portal, and this is how our course is broken down into. We'll be having Carsense assignments done in the portal, so kindly note that, but the exam will be face-to-face. So I would expect that once we have an assignment, or I post a forum, it's the duty of the student to ensure that you respond to the forum during the class timings. So our class will be on Thursday from 5 to 8. And therefore, during that time, any forum that is posted in the portal, we are supposed to respond to. Should you have any query or pressing issue, I'm always reachable on my phone. So I want to introduce calculus. And I've said calculus is concerned with the mathematical analysis of change and movement. And there are two operations that are involved. We have differentiation and we have integration. And these two operations are a reverse of one another, just like the addition to subtraction or multiplication and division. We'll be coming to that, and you'll see how one is the reverse of the other. When we are talking of the change, if I am to take you closer home, I know you understand the concept of gradient. And when we are talking of the rate of change, if I have two, let's say I have two functions here, two equations, y is equals to 4 plus 3, and I want to draw that line from -1 to 4. So if I was to replace my x with the -1, I'll get 1. I replace it with 0, I get 4. I replace it with 1, I'll get 7. I replace it with 2, I'll get 10, and on and on. Same case to the second function here. Y is equal to -1 plus 3x will give me these figures. So if I plot these lines on a Cartesian plane, I'm going to get such a graph. So the first graph is for the function y is equal to 4 plus 3x. And the second one is for y is equal to -1 plus 3x. On a keen look, we can say that the two lines are parallel to each other. But the reason why these two lines are parallel to each other, it's because of their gradient. So you can see the gradient. When we put our line in this form, we call this form in the form of y is equals to a plus bx. Our b is the gradient. We're just referring to the basics of mathematics. And b is our gradient. So b, how do we get the gradient? We normally get the gradient by looking at the change in y values over change in x values. So if I was to go, let's say, pick two points here. For example, let's say I pick point 3. So when x is 3, my y is 13. If I pick another point, let's say 0, when my x is 0, my y is 4. So if I were to get the change, 13 minus 4 is equals to 9. 3 minus 3 is equals to 3. So my change in y over change in x will be 9 divided by 3. 9 divided by 3 will give us 3, which means my change in y over the change in x, when x changes by 1 unit, my y changes by 3 units. So the slope or the gradient, the slope, what we call the b, is given by change in y over change in x. And you said it's like when x changes by 1 unit, my y changes by 3 units. That is for linear function. So we can easily say for a linear function of the form y is equal to a plus b, we know that y is the, y is the dependent variable, then x is the independent variable. And we normally say that a is the y-intercept, or where the line is cutting the y-axis, whereas b is the gradient. That is for the straight line. So we are looking at the rate of change of a straight line. Now, when we come to the nonlinear functions, I want to illustrate. For the straight line, is very easy. But if I was to give you such a scenario, you can see what we have. So I have a curve that is moving from D, A, all the way, this should be B to C. Now, the slope of this function is very hard to tell the gradient. But you can easily say from D to F, the gradient is positive. From E to A, you cannot even explain. But from A to B, we can say it's negative. Again, from B at some point, it's going up. So what we normally do in calculus, we help get now the gradient of this line at a given point. That is the use of calculus. And that's why you say that calculus is concerned with the mathematical analysis of change or movement. So our function is moving up, down, up, down. If we were to get point C, we need now to be assisted by calculus to be able to do that. And we do that by what we call the concept of limits. This will bring us to the understanding of differentiation in an easier way. For example, if I say that y is equal to x plus 2 as x approaches 0, let me present a better, allow me to present a better, let me stop sharing this. I want to share the, hope I'm sharing the, hope on your screen you can now see the limits, right? Very well. I want us to take it easy. It's not complex. So the meaning of x tends to A is written as this form. So this arrow means that our x is tending to A. So we are talking of the numerical difference between x and A. For example, if x, let's say, is 5 and A is 6, or if we say, for example, let me not give any, when we are talking of x tending to A, it means that it can be made less than any positive quantity to approach that A. In the second case, for example, when I say x tends to 0, it means that I'm trying to decrease numerically the value of my x to tend to 0. Let's say it was 5. When it is tending to 0, it can go to 4, 3, 2, 1, 0.8, 0.3, 0.001. You get, we are tending to 0. Then I have the meaning of x tending to infinity. When x tends to infinity, it means that I'm increasing the number of x infinitively, endless, to forever, right? Calculus initially, it was discovered all through the works of the scientists. We were able to come up with calculus, and they were doing these validated tests to try and understand or solve scientific problems. But calculus is being used in nearly all fields. You can say it is the language of the world. And mathematics basically is what is sorting out many of the problems, right? So we are talking of a number L is said to be a limit of the function of x as x is tending to A. And that is what we are writing here. Now we do have different properties that helps us now arrive at this. For example, I have the first one. So when I'll be talking of the limit, I wanted to establish when I talk of the limit of x tending to A, I'm talking of the numerical aspect of x and the A. So one is approaching the other. The first property is when the limit of x is tending to A for a constant b, then the limit of a constant b will remain at b, or will remain as b. The second one, let me give an example. Good to work with the numbers. Let's even not try to follow the principles. We'll come to the principles later. For example, look at these limits. When I talk of the limit of x tending to 2, it means that I want to replace, or I shall replace my x with the 2. So if I replace my x with the 2, then it means that that function will be equal to 2. When I talk of the limit of x tending to 1 in a function of the form 5x plus 2, then I'm going to substitute my x with 1. Therefore, I can say the limit of that function will be tending to 5 into 1 plus 2, which is 7. In other words, I'm saying the limit of the constant 2 is still constant because we don't have an x. At this point, we say our x is raised to 0. You know that x raised to 0 is equals to 1. So 0 is very important in limits. And I'll be explaining why later on when we'll be doing now the differentiation, right? Look at the third example. The limit of x tends to -3. So I'm going to replace all my x's with the -3. For the first case, if we replace, -3 squared is 9. So 4 multiplied by 9 give us 36. Then I have -3 multiplied by -5. Negative multiplied by negative is positive. So I'm going to get positive 15. And then my 1 is a constant. It will remain as a constant. I explained the fourth scenario. The fourth scenario is a scenario of product. So I have two functions here. I have the first function, 10x squared minus 1. And the second function is 2 minus 3x. So the solution is to replace, then I open the bracket. It is as simple as that. So this is how we apply this property. So my x I've said is tending to -1. So -1 squared is 1. So that will be 10. Then 10 minus 1 will give me 9, right? Then I go to the second one, 2 minus 3x. X is -1. -1 multiplied by -3 will give me 6, right? Are we there? So it's -1, sorry. So it will be -1 multiplied by -3 will give me negative, will give me positive. Negative multiplied by negative will be positive. So -3 multiplied by -1 will give me +3. So 2 plus 3 will give me a 5. Then I multiply, is a product. So the property needs you to work body mass. You first work what is in the bracket. Then you multiply. So for the product, I'll get 9 multiplied by 5, which is 45. And then I go to the fifth one, which is a quotient or division. So I'm looking for the limit of the function 6x minus 7 divided by 1 minus 2x. I again replace. So it will be 6 multiplied by 5, which is 30. 30 minus 7 is 23. I do the same for the denominator. 1 minus 2 of x, which is 5. So it is 1 minus 10, which gives me -9, right? Then I get now the limit of a power. If I have the, I have a function that is raised to a power. It will be so tedious to try and work this in that form. Later on, we are going to equate the whole of this function, which is in the bracket, with a u. But at this level, what you're supposed to know is, as the limit of our x tends to a of the function of x raised to n, what we normally do is to work what is in the bracket, and then we raise by the power, which is our n. So we go, so this will be 2 into 3, and our x is 4. So that is 12, and then minus, so 2 plus 12 minus x squared. Our x squared will be 16. So I'll be talking about 2 plus 12, which is 14 minus 16, right? So I'm going to get -2. If I square my -2, my answer will be 4. So notice that we have worked what is in the bracket, then raised to the power. It's easier that way. And the last principle is when now it is raised to a fraction. And raising it to a fraction means this is where now later on we are going to introduce surds. But what I need you to know is that we still work what is in the bracket by replacing our x. So our x is 4 raised to x So 4 multiplied by x, which is 7, and then you are going to have the 7 cubed. If you work this out, you are going to get 371. Then 371 raised to a third. You can leave it at that point. The scientific calculator will be able to give you the granular, but in calculus, the most important thing was for us to solve for the limit. Now, when we are tending to infinity, it means that our x is increasing to an indefinite form. So we cannot explain indefinitely where it will be headed. So for the limit of x tending to infinity, we divide the numerator and the denominator with the highest power of x, which appears in the denominator. And note that our x is tending to infinity. So if I have 1 over x squared, it will be 1 over 1 million, 1 over 1 zillion, and on and on and on. In other words, you are saying that this will be tending to 0 as our x is tending to infinity. So our x is tending to infinity, the whole of this fraction will be tending to 0. In other words, we are increasing our denominator. As we increase the denominator, it means that our answer is decreasing. It's like dribbling a ball. If you dribble a basketball, it will dribble and then the intensity of the dribbles will go reducing. Scientifically, that ball will never come to a stop. It's only that your eyes cannot be able to see. So we are talking of such a scenario. Are we there? So if that is the case, now see, let me give an example. So we are talking of the limit of x tending to infinity. If that is the case, I'm going to divide the highest power of x in the denominator, which is our x. So in this case, you can see 2x plus 1. So it will be 2x over x plus 1 over x. Then 3x over x minus 4 over x, because my x is tending to infinity. And we said, as our x tends to infinity, the whole of this function will be tending to, you can see the whole of this function, where x is increasing at an indefinite rate, will be tending to 0. In other words, we are working out for the fraction. Now, for this case, 2x over x, x will cancel, so I'm going to be left with 2. 3x over x, my x will cancel, I'll be left with 3. But this particular fraction will be tending to 0. So you can now see what I've indicated here, that as our x tends to infinity, the fraction that will be arising will always tend to 0. Are we there? Look at the second one. 1 over 6x plus 7. Again, I'll introduce my x by dividing by the highest power of x in the denominator. So 1 over x, which will give me 0. And then I have 6x over x, that will give me 6, plus 7 over x, which will again tend to 0. So my answer will be 0. 0 divided by any number is 0. I have another example here. Get the solution of this. Again, introduce the highest power of x in the denominator. So I think now it's becoming easier. So it is 10x divided by x. You cancel out the x's, you're going to get 10. Then minus 24 over x, which tends to 0. And then I have 5x divided by x, which is 5. Our answer will be 2. Look at the following. So I have can see I have quadratic equations of the form x squared minus x minus 2 all over 2x squared plus 3x minus 7. Again, dividing by the highest power of x in the denominator, I'll be replacing. My x will be cancelling out. I want you to appreciate that the highest power of x in our case here is x squared. Can you see that? It's no longer x, it is x squared. I'll be dividing everything with x squared. If I divide everything with s squared, I'm going to have such a scenario. So I'll cancel out my x's, and whatever is divided by x, of course, will be tending to 0, and the answer will be a half. In other words, we are saying that if you divide by the highest power of x in the denominator, you're able to get the limit of that particular function as x approaches to. I'll be sharing this note, you can refer, but basically we are dividing by the highest power of x in the denominator. The reason why I'm introducing the concept of limit is for you to understand that in derivative, for us to be able to operationalize the calculus, we got to let our x be defined, right? Like for instance, in the first properties, all the properties I've given. Now we can come to the properties. It's easier now to understand when we are coming from Skoda deductive approach, from the known to unknown. So we can easily appreciate, right? And later on, I'll be introducing the natural logarithm. I don't want to introduce them this early. I wanted first us to appreciate that when we talk of the x, we are talking of two things, not two, they are three. So I first said when my x is tending to a, we are getting the numerical difference in a manner that any positive quantity, however small, we are going to talk of x tending to it. Could be 1, could be 0.00007. We are talking of the smallest numerical difference of x towards that constant a. When I'm talking of x tending to a, it is decreasing numerically until such a point where it will reach 0. And when I talk of x tending to infinity, it will again increase numerically to an indefinite positive quantity. It's a wrap. I wanted to introduce calculus. So in our next class, it will be easier now for us to operationalize the tool and try to sort out the problems, the day-to-day problems in the world or the society. Enjoy your day. Should you have any query, any question, drop it in the portal. I'll be responding. Equally, I'm going to give you an exercise or a forum where you are supposed to test the understanding of what we've undertaken today. Thank you very much.